This video will cover section 12.1. Sequences. Now, chapter 12 is about sequences and series. At the end of chapter 12, we'll meet the binomial theorem. Today's lesson is going to be 12.1. 12.1 is an introduction to sequences. An introduction to sequences. We'll learn about specific sequences, the arithmetic and geometric sequences in later sections. But today we're just going to talk about sequences in general. What is a sequence? So we're going to begin with a definition. Because if we don't know what a sequence is, then it makes no sense to study sequences. So we begin with the definition of a sequence. The definition says this. It says a sequence is a function. And I'm going to pause right there. That's not the whole definition. That's not the complete definition. But I'm going to pause there because this is the most important part of the definition for us. When we start talking about sequences and when we first begin to learn about sequences, we think we're learning something new, something different, something we haven't encountered in the past. However, that's not the case. What we're working with here is a function. We have spent, this is chapter 12, we've spent the previous 11 chapters of this book discussing functions. We know all about functions. We can graph functions. We can find the domain. We can find the range of a function. We know if a function is continuous. We know if a function is increasing or decreasing. We know if a function is even or odd. We have all of this information that we have gleaned over the prior experiences in math classes about functions. Sequences are just functions. That's the first thing we all have to come to grips with. As soon as we accept that and try not to make sequences into anything more complicated, then and only then does this chapter really become as approachable as it should be for most of us. So let's make sure that we accept, before we begin, this statement. A sequence is a function. It's just a function. That's all it is. It's nothing more than that. The definition goes on and says, whose domain, whose inputs, right? That's what the domain is. The domain is the inputs into our function. Whose domain is the set of positive integers. Now right there, we get to a second important characteristic of sequences. Sequences, if we summarize this definition, sequences are functions, and the only numbers we're allowed to plug in, the only inputs we're allowed to have, are the positive integers. In other words, sequences are functions who have a domain that's nicer than the domains we typically work with. Consider this. F of x equals x squared, right? This is a function that we all are perfectly comfortable with. We know this function. We know the graph of this function is a parabola that opens up. So this is the graph. We know the domain, right? We all know that that's not how you spell domain. We know the domain of this is the set of x's such that x is an element of the reals. Any number on the number line can be plugged into this function. We can plug in 1, 2, 3, 4, -1, -2, -3, -4. We can plug in 1/2, -1/2, 1/10, -1/10, 0, pi, the square root of 2. We can plug any number into this function, and we're comfortable with that. That doesn't frighten us. We know what the range is, right? We can look at the graph. We can say the range is the set of y's such that y is greater than or equal to 0. We can say that f is increasing on 0 to infinity, right? We understand functions can be increasing, decreasing on intervals, and we know this function is increasing on this interval. It's going up to the right. We can also say f is decreasing on negative infinity to 0. The function is decreasing over here. It's going down to the right. We've even discussed continuity. We could say f is continuous on negative infinity to infinity. We discussed continuity. We said when is a function continuous? And we said a function's continuous if you can draw it without lifting your pencil. We're going to expand on that definition of continuity as we move through the book, but right now we can say that. We know f is an even function. And why did we say that? Because we have y-axis symmetry. Now, this is just the information we can state, and there's more than this, of course, regarding this function. We've learned all of this in Algebra 1, Algebra 2, and the beginning of Precalculus. The opportunity to pick a number to plug into this function is endless. We can pick any number we want. That number can be a decimal, that number can be an irrational number, that number can be a fraction, it can be negative, it can be positive. How are sequences different than this? Well, sequences are different than this in a very important way. Let me get this out of the way. So how are sequences different than just the function I just wrote on the whiteboard right there? How are they different? Well, if we read the definition, first of all, it says a sequence is a function. So we could have a sequence that looks like x squared. However, the domain is not all the reals. The domain is the positive integers. We know what that means. That means 1, 2, 3, 4, and on we go. We're only allowed to plug in 1, 2, 3, 4, 5, 6, 7, 8. That is so much nicer than what we just saw earlier. Now, if we were going to try to express the sequence x squared, one of the things that may cause us to be a bit confused is notation, right? If I write this is a function like we wrote functions back in an algebra class. Our notation is f of x equals x squared. We're all comfortable with that notation. We know the input goes here. We know the output is over here. And we understand this notation. This notation brings us a degree of comfort. However, what does the notation look like for a sequence? Well, we have to tell the reader that we're talking about a sequence and not just a general function from Algebra 1 or Algebra 2. And the way we do that is we come up with a different notation, a notation that says, hey, this is a sequence. So we're going to move away from our f of x notation, which, if you think back to your Algebra 1 days, you started with y equals x squared. You didn't have that notation. You learned that notation. You're comfortable now with that notation. Therefore, you should be able to learn another notation and then become comfortable with that notation. Just like this was new on a certain day in Algebra 1, today is the day that this notation becomes new for us. This is our notation for a sequence. This is what it is. We write it like this. We put a bracket, we put a term in here. We call this A sub n, right? That's how we say that, A sub n. And then we write n squared. Okay? Now, what does that tell me as a person who understands the notation? What is it going to tell you as someone who's going to learn the notation? I'm going to see this, and I'm going to think to myself, oh, there are brackets. There's no F or G or H. There are brackets, so that means it's a sequence. That's what the brackets mean. The brackets mean we have a sequence here. Now, what do I say to myself when I see those brackets? I don't say, oh my goodness, I'm going to panic, it's something new. I say to myself, this is even better than this. I take the optimistic approach. This is better than this. This is a function, see, is a function, and the domain is 1, 2, 3, 4, 5, 6, 7. I don't have to plug in 0.6. In fact, I can't. I don't have to plug in pi or -8, for example, because I can't. The domain is just the positive integers. So, what does this sequence look like, right? What can we write for this? Well, just like functions, we can do a t-table. We can do a t-table just like we did back when we were first learning functions in Algebra 1, Algebra 2. We made a t-table. We can make a t-table here. Okay? Our t-table here, though, is going to look a little different. We're going to have n, and over here we're going to have a sub n. Now, our t-table, when we first met our t-table back in algebra, it had an x and a y. Nobody panicked about that. Nobody said, why is the x over here? Why is the y over here? We were told these are the inputs, these are the outputs. So we can make a t-table. And what are we allowed to plug in? Well, unlike functions in Algebra 1, we're only allowed to plug in 1, 2, 3, 4, 5, 6, 7, and on, and on, and on. Now, what is our output going to be? Our output's going to be given to us by the formula over here, just like it was given to us by the blue formula up there. We know we're going to take n and we're going to square it. So what are we going to get for an output? We're going to get 1. What are we going to get for an output of 2? We're going to get 2 squared. That's going to be 4. What are we going to get for an output with 3? We're going to get 3 squared. That's going to be 9. And what are we going to get for an output of 4? We're going to get 4 squared. That's 16. Okay. Now, our first learning objective in Chapter 12, Section 1, our first learning objective says, write the first several terms. So our first learning objective is to write the first several terms of the sequence. And we have done that. You and I have done that right here. We've written down the first several terms of a sequence. Now, these are ordered pairs. They're ordered pairs, just like back in Algebra 1. They're ordered pairs, just like in Algebra 1, they were ordered pairs. Nothing is different. It's still just a function. So these are ordered pairs. So one way that we wrote functions down back in the beginning, not that anybody remembers because it was way back in Algebra 1, is we said, well, what do my ordered pairs look like? Well, my ordered pairs here are 1, 1, 2, 4, 3, 9, 4, 16, and they just keep going, right? So we can express these sequences, which remember are just functions, We can express them in a t-table. We can express them as ordered pairs. However, because we are always looking for the most efficient way to write things, that's what we're looking for, the most efficient way. When we considered this back in Algebra 1, we had to write it this way. We had to write our ordered pairs. We needed the x and we needed the y. However, if you take a look here, there is a pattern, a very definite pattern in our x's. When it comes to sequences, there's a pattern. We're going to use a 1, right? Then we're going to use a 2. Then we're going to use a 3. Then we're going to use a 4, etc., etc., etc. So instead of writing a sequence like this, we often skip the inputs. All right? We often skip the inputs. What do I mean by that? Well, we know what the inputs are going to be. So instead of writing all of this, what you'll see written, change out my blue pen here. What you'll often see written for a sequence is something that looks like this. 1, 4, 9, 16. Now, what have I written there? Have I written the x's or have I written the y's? Have I written the domain or have I written the range? You're correct. I've written the range. We only list the outputs. Now, that's not something that should cause us confusion. That's something that should give us clarification. Because if I've only listed the outputs, and I have my brackets, that tells me specifically I'm working with a sequence. These are the outputs. So one of the things that causes us to be confused about sequences is they look different. Now, the only way we're going to overcome that is to remember the definition. A sequence is just a function whose inputs are so predictable that we don't even write them down. Now, a sequence is a function. That means I can graph it, right? We can graph a sequence. What does this sequence look like? Well, we have a dot at 1, 1, right? We have a dot right here at 1, 1. Then our second dot is at 2, 4. Right? Second dot is here at 2, 4. Our third dot is going to be at 3, 9. Right? Our fourth dot is going to be at 4, 16 up here someplace, right? Now, don't give in to the temptation of connecting the dots. Right? We're not doing it dot to dot like we did when we were little kids here. We are graphing the sequence. This is the graph of a sub n equals n squared. The sequence a sub n equals n squared. That's the graph of the sequence because the only thing we have are inputs of 1, 2, 3, 4, 5, 6, 7, etc. Now, I'm spending a lot of time on this. I mean, we're up to almost 20 minutes because this is the most important part of sequences. If we can get our heads wrapped around the fact that I'm just working with functions, that's all I'm doing. And the function I'm working with is way nicer than the function I worked with in Algebra 1. It's much, much more approachable because of the limitation in the domain. We can just write an example over here. We can say something like this. I have the sequence. I'll call this one B sub n. We typically use A's and B's to name sequences. F's and G's and H's are reserved for functions. A's and B's are sequences. We could say our sequence is going to be n plus 1 over n plus 2. Right? Whatever I write, we call this the general term here. Whatever I write, that's my output. My inputs are not stated because I know it's a sequence because of the brackets. That's my symbol. So I know it's a sequence. So now I know what my inputs are. What does this sequence look like? Right? What does it look like? Well, I'm going to plug in a 1. When I plug in a 1, I get 1 plus 1. That's 2. Right? I plug in a 1, I get 3 on the bottom. Comma. Now I plug in 2. My inputs are 1, 2, 3, 4. That's all there is to sequences. So I plug in a 2. I get 3 on the top. I get 4 on the bottom. Now I'm going to plug in 3. 3 plus 1 is a 4 on the top. 3 plus 2 is a 5 on the bottom. And if you look, there's a very, very discernible pattern here, right? A predictable pattern. We know our next term is going to be 5 divided by 6. Our next term after that is going to be 6 divided by 7, right? And on and on and on. Now remember, these are just the outputs, right? These are just the outputs. This is range values only. Why didn't we put down the inputs? Because we all know I inputted a 1 there, and a 2 there, and a 3 there, and a 4 there, and a 5 there. Okay? We know that's what I inputted because of the fact that it's a sequence. I know those people were the inputs. Now, from here, we like to be able to name each of these. You know, I don't want to say this is the third one and this is the fifth one. The way we name them is we say, okay, this is my sequence B. So this is the first person in my sequence. So I'm going to call that B with a subscript of 1. That's my first B. This one's going to be my second B. So that's B with a subscript of 2. This is my third B. So that's B with a subscript of 3. This is my fourth B. And on and on and on. Okay? So that wraps up our first learning objective. Our first learning objective is to write out the first several terms of a sequence. We did it here with this sequence. We wrote out the first several terms. We did it here with this sequence. We wrote out the first several terms. Okay, so that will get you started with the beginning of your homework. Now, let me clean this off. I'm going to leave that definition up there just so we can refer back to it as we move through this whole lesson. We want to just keep reminding ourselves, we're just talking about a function, right? It's nothing new, it's nothing different, it's just a function. So what's our second learning objective? Well, one way, right? One way to write a function is to do what we've done. You plug in a 1, you plug in a 2, you plug in a 3, you plug in a 4. Now, I'm going to remind you of some notation that you encountered back in Algebra 2 that I want to make sure that you haven't forgotten, all right? So let's review factorials. Now, if you remember factorials, that's something that looks like this, 4 with an exclamation point. That's a mathematical symbol when we write it like this. And what does that tell us? That tells us I'm going to take 4. I'm going to go down by 1. I'm going to get 3. So I'm going to multiply 4 times 3. I start with 4. I go down by 1. I get to 3. I go down by 1. I get to 2. I go down by 1. I get to 1. So 4 factorial means 4 times 3 times 2 times 1. So we get 24. Okay. Now, there's a couple of things about factorials we need to make sure we're clear on. This is how factorials work, right? By definition, 0 factorial is equal to 1. I understand that doesn't fit my little rule up here, but if I don't define 0 factorial to be 1, then all the math we're going to do in sequences and series don't work. So that's just a definition. 0 factorial is 1. 1 factorial, well, how do you count down from 1? Well, you start at 1 and you stop. So 1 factorial is 1. So in general, what does n factorial look like? Okay, what does that look like? Well, n factorial, we start at n. We go down by 1, and we multiply. We go down by 1 more. So if we've gone down by 1, the next time we go down by 1 is going to be 2. We subtract another 1, so that's going to be 3. And this keeps going until we eventually get down to 4 times 3 times 2 times 1. Okay? So that's our rule when we get to 2 on. Our rule for 1 is right here, and our rule for 0 is here. So what's our rule that this tells us what to do at 0, this tells us what to do at 1, this tells us, all right, we're going to start at 2, from 2 down, this is what we do, right? Now, one more little trick to factorials. Maybe this is going to be clear to you, maybe it's not. 5 factorial, right? That's 5 times 4 times 3 times 2 times 1. Sometimes we want to cancel, simplify factorials. Well, there's I think if we take a look at this, 5 factorial is 5 times 4, 3, 2, 1. 5 factorial is 5 times 4 factorial. So we can say n factorial is really n, and then that's times n minus 1 factorial. We're going to need that every now and then to simplify some of our problems. Okay? So one way that we can write sequences is we can just list them based on the general term. We've done that. We've just completed that. Another way we can talk about sequences, and that's our second learning objective. Our second learning objective is to write the terms of a sequence So we want to write the terms of a recursive sequence. A recursive sequence. Now, what does this mean? Well, it's a different approach. It's a little different approach. How is it different? Okay. We are not, let's talk about how it's different first. We are not given a general term. Now, remember, a general term looks just like f of x. It's a little different because, of course, the general term would be something like, b sub n equals, and then we'd be given that. So if we can accept that this is the way to write a function that we call a sequence, then this just looks like f of x equals. Recursive sequences, we're not given that. What are we given instead? Well, what we're given in a recursive sequence is our givens here are the first term and a formula for the next term. Okay, so write that down. And then we'll look at an example, right? We'll look at an example. So what would a recursive sequence look like? We'll do an example. We'll do it right over here. They'll tell us something like this. They'll say, well, the first term, a sub 1, right? A sub 1, that's our notation for the first term. Our first term is going to be 1. And then they're going to say, well, your next term, your nth term, right? Your nth term is going to be n times the term that came before that term. Now that's going to take a second for us to realize what we're saying here. So let's take a closer look at this. If n is 3, we'll just write that right here. This is going to be a sub 3. N equals 3, right? That's what we're going to do. We're going to let n equal 3. Now, if you're wondering why did I let n equal 3, I just picked 3. I could have picked 7, but I picked 3. Let n be 3. So what does a sub 3 look like? Well, based on this is n and this is n, it's going to be 3 times the term that came before a sub 3. A sub 3 minus 1. If we simplify that, that's 3 times a sub 2. So to find a sub 3, I have to know a sub 2. And this is the kicker to recursively define sequences. If I want to know the third term, I have to know the second term. By a similar argument, if I want to know the 23rd term, I have to know the 22nd term. The problem is they only gave me the first term. So how do I find the third term? Well, before I can find the third term, I have to go find the second term. So what is a sub 2? Using our formula, a sub 2, n is 2, this is going to be 2, and this is going to be a, and this is going to be 2 minus 1. Now, most of the time we do this in our head, but I'm writing it out because we're learning the first time through here. So this is going to be 2 times a sub 1. Now, they told us a sub 1, so that's 2 times 1, that's 2. So a sub 2 is 2. And if you're thinking to yourself, this takes a little more work than the general term did in the previous learning objective, you're correct. It does. It takes a little bit more effort to do this. So how are we going to find a sub 3, right? What are we going to do to find a sub 3? Well, to find a sub 3, based on our formula, we've already written it right here. It's 3 times a sub 2. So what do we get for 3 times a sub? Well, we just found a sub 2. So this is going to be 3 times 2, and that's going to be 6. To continue, how are we going to find a sub 4? Well, we're going to use our rule here. N is 4, so we're going to get 4 times a sub 4 minus 1. So that's going to be 4 times a sub 3. We just found a sub 3. So that's going to be 4 times 6, or 24. Now, the problem with recursively defined sequences, right, is if someone asks us to find a sub 11, what do we need to know? We know that's 11, right? Using our formula, this is an 11, so that's an 11, n. But then that's times a sub 11 minus 1. That's going to be 11 times a sub 10. We don't know a sub 10 yet. So recursively defined sequences take a little more effort, right? It's not hard. No one said it's difficult. I said effort. It takes a little more effort to find this term. We would have to go backwards and find a sub 10, and go back, of course, to find a sub 10. We need a sub 9. To find a sub 9, we need a sub 8. To find a sub 8, etc., etc., etc. Okay? So that's our second learning objective. Writing out the terms if a sequence is defined recursively. All right, so I'm going to clean this off. And we'll go on to our third learning objective. Right, our third learning objective. What is our third learning objective? Well, our third learning objective is to use summation notation. Now, this is when it happens, okay? We all know it hasn't happened yet for most of us. So this is when it's going to happen. we're going to learn how to use summation notation. Summation notation is the capital sigma that most of us have been avoiding, right? We write it down when our teachers write it down. We write it down when it's in the book. But a lot of us haven't yet come to grips with what this means. So let's just do a quick example. We'll start with an example. This is typically how summation notation works, right? We have a symbol, sigma, that's capital Greek letter sigma. So we have sigma, k equals 1 to 5, and they put something in here. Let's just make it real simple. We'll write k here. Okay. Now, what does this mean? First of all, sigma means to add, right? This means to add. That's what sigma means. So the one way we can remember that is sigma starts with S, sum starts with S, so sigma means to add, right? Sigma means to add. Now, we call this an index, right? That's what we call this. We call this an index. In this problem, my index is starting at 1, and it keeps going up until it gets to 5. It goes 1, 2, 3, 4, 5. That's how the index works. It's a counter if we want to think about it that way. So what does this mean? This tells us what we're going to add. So how would we rewrite this? Well, k starts at 1. All we're doing is putting a k there, so that k starts at 1. I put a plus because sigma means sum. K now moves from its beginning value of 1, it moves up to 2. So now I put a 2 because all I have is a k. Now I keep going until I get to 5. So after 2 comes 3, after 3 comes 4, and after 4 comes 5. So a sigma notation helps us add, right? So we get 15. Let's do another example, right? We'll do another example. This time we'll use I for our index because sometimes we use k, sometimes we use I, sometimes we use j. So this time I'll let I start at 2, and I'll go until I is 4. Okay? And we'll say that we're going to have 3i minus 2 here. Now, what does this mean? Don't panic. It doesn't mean anything complicated. We start when I is 2, right? Now, I'll write it out. Normally, we do it in our heads, but I'll write it out because we're learning. If I is going to be 2, my first thing is going to be 3 times 2, right? I is 2 minus 2. Now, I have a sigma sign, so I go plus. I started at 2. My next number is 3. So I would have 3 times 3 minus 2, and I go plus. I started at 2, I took care of 3, now I go to 4. Now I'm going to stop at 4. 4 is my top value, so that's where we stop. So that's going to be 3 times 4 minus 2. Again, normally we would just do this in our heads, but we're learning, so we're writing it all down. 6 minus 2 is 4. 9 minus 2 is 7. 12 minus 2 is 10. And so what do we get there? We get 21. Okay. So we want to become comfortable with the sigma notation. What else could we do here? Well, we could do something like this. K equals 1 to n. Maybe we just have a variable as our stopping point. And we'll put our friend k factorial in there. Now we start at 1. So that's going to be 1 factorial. Plus, now we move up to 2, right? We start at 1, we go up to 2, so that's going to be 2 factorial. Plus, we go up to 3, we get 3 factorial. And we keep going until we get to our stopping point, which is going to be n factorial. Now, unlike this problem, where we got an answer of 21, or this problem where we got an answer of 15, we can't find this answer because we don't have a value for n. So I can't actually get this to equal something. This would be my answer. Okay? Now, there are some rules about sigma notation that we have to learn. This is the place right? This is the time, I mentioned that a few minutes ago, this is the time when we're actually going to go, okay, I'm going to learn this sigma notation. It's going to happen right now, today, in section 12.1. This is where you're responsible for learning sigma notation. So here are some properties. Properties. These are like our trig identities for sigma notation, or our log rules for sigma notation. So it says, if you have a sequence, a sub n, now remember that's just a function, right? It says so right there, a sequence is a function. So we just have a function. And another one, b sub n. So if these are sequences, and C is a real number, then, all right, what do we know? We know that if we have the sum k equals 1 to n of a constant, right, times a sub k. Now what does that mean? We have like, well, we have like 2 times whatever this is. Just like right here, we had 3i. Nobody was overpowered by 3i. We went 3 times 2, 3 times 3, 3 times 4. That's all this says. We have a constant. 3 was our constant here. Here our constant is c. So we're just talking about it in general. What is this going to look like? Well, this is going to look like c times whatever we got for a1. Right? We start at 1, we plug a 1 in, plus c times whatever we got from a2, plus c times whatever we got from a3. And this is going to keep going until we get everybody gets multiplied by the constant, doesn't it? Constant times a1, constant times a2, all the way to a sub n. Well, if you take a look at this, you could factor out the constant, right? We know that from algebra 1. And if we take a look at this piece, right, this piece, that's really c, and then what's left there is a simpler version of the summation. So what does this property say? This property says, right, this is what you want to write in your notes, this property says we can factor constants out of summations. That's what it says. It says we can factor out constants. That's what we did. We factored the constant out. What else do we get for a property? Right? What else do we get? Well, we get this one. What happens? K equals 1 to n. What happens if I have 2 terms in here? If I have 2 terms, well, we could write this. We could write this like this. A1 plus B1. Right? Plug in 1, A1, B1, A2, B2. All the way to AN, BN. We could do that. That's perfectly allowed. That's what the rule says. These guys are grouped, so we'll just group all these up. But these are all pluses. We can rearrange them, right? We can rearrange them. We have the commutative property of addition. We can rearrange them. This really looks like this. That's not rearranging them. It's writing them the same way. We could put all the A's together like this, and then we could put all the B's together. But what is that? That's the sum of the A's. That is the sum of the B's. So we could, if we wanted to, we could add them up like this, or we could add up the A's by themselves, do that first, and then add up the B's by themselves, and do that second. The choice is ours. The choice is ours. Now, this property also works if you subtract. So I'm not going to rewrite the whole problem again, right? That would make this a minus, and it would make this a minus. Now, the last useful, well, there's more than one to go. I didn't mean to get anybody's hopes up there. But one more really nice property. I'll write it over here, and then we'll have to erase the whole board. I'll write it over here. What happens, right? What happens if we have, well, this? Now, if you take a look at this, we started at 1, we went to J. Then we went from J plus 1 to N. So I'm going to write that right there. And I'm just going to leave that there to stew for a couple of seconds. And then I'm going to clean off some space. And we're going to try to make some sense out of that property. Because that's one of those properties that, for a lot of us, we look at that and we're like, I don't know what's going on there. But that's okay. That's all right. My job is to make you understand what's going on there. So let's see if I can pull off my side of this, right? Your side was to write it down and say, hey, I'm lost. I don't get it. My side is to make it make sense. So let's see if I can do my part. Okay? So what's this saying? All right? Well, here we go. I'm going to show you what it says. Here's an example of how that property works. What happens if I wanted to go from k is 1 to 5 of 2k plus 1? What this property says is we can go from 1 to 5. Right? We can do that. We can do it. We'll do it in our heads. We plug in 1, 2 times 1. K is 1. 2 times 1 is 2 plus 1. 3. K goes to 2. 2 times 2, 4, correct, plus 1, 5. Yep. K is 3. 2 times 3, 6, plus 1, 7. I get it. I see the pattern too, but we're practicing. K is 4. 4 times 2 is 8. 8 plus 1 is 9. K stops at 5. 5 times 2 is 10, plus 1 is 11. Now what do we get here? Now we get 20 plus 30, or plus 10 is 30, so we get 35. Again, how, Kevin, does this have anything to do with this? Well, here's how it has to do with that. What this property says is, if we wanted to, we could have done this in pieces. We could have gone from k is 1 to 3. And then picked it up, right? This is going to be my 3. And then pick it up back at 3. But we don't want to start at 3. We want to start at 3 plus 1. We don't want to overlap. So we're going to go from 4 to 5. That's what the property says. It says we can take a sequence, a sum that goes from 1 to 5, and we can write it as the sum from 1 to 3 plus the sum from 4 to 5. Now, what would this look like? Well, let's take a look. We put a 1 in here. That's 2 plus 1. That's going to be 3. Right? We put a 2 in here. That's 4 plus 1. That's going to be 5. We put a 3 in here. That's 6 plus 1. That's 7. Right? I'll put brackets around it because that's this piece. Plus, what do we get over here? Well, we put a 4 in here and we get 9. We put a 5 in here and we get 11. We get exactly the same answer. That's what this property says. It says if you want to, right? If you want to, you can split it up into pieces. Now, why would I want to do that? Well, the reason you'd want to do that is because maybe on a test, we ask you, what is this? Well, you know what this is. That piece right there is going to be 35 minus this piece right here. So maybe we don't want to calculate the whole thing. Maybe it's not 4, 5. Maybe it goes from 4 to 500, right? Maybe it goes from 4 to 500. So we don't want to write that out. But I tell you on the test the answer. So you put the answer here, you take off this piece, it's got to be the other part. Okay? So what other properties do we have here? Let's see, we've got a couple more. What's it look like if we go k equals 1 to n and we add up a constant? Now notice, there's no k here. This is not a variable, this is constant. So what is that going to be? Well, I plug in 1. There's nowhere to plug in 1, so all I get is c. I plug in 2. There's nowhere to plug in 2, so all I get is c. I plug in 3. There's nowhere to plug in 3, all I get is c. And I keep doing this until I get to the end. Well, that's n times. We did that n times. We put down n c's. In other words, that's n times c. All right? That's what our 3rd grade teacher used to teach us how to multiply back when we were 8. She said if you add up 7 4 times, right? If you add up 7 4 times, she told us that's really 4 times 7. That's what multiplication is, repeated addition. Now, here are 3 very important. I'll change colors. I'll write these in green. These are very important. Okay, I said they're very important. I mean they're very important. You want to know these 3. Okay, sine squared plus cosine squared equals 1. We all learned how important that was. We want to know these 3 that I'm about to give you right now. What happens if I add up k equals 1 to n of k? Now, we did an example earlier with this, right? What does this look like? This looks like 1 plus 2 plus 3 plus 4 plus n. Now, you may remember from Algebra 2, there's a formula for this. Right? There's a formula. We want to know this formula. We're going to learn this formula later in Chapter 12. We're going to learn where it comes from. Right now, we're just going to write it down. The formula says this is n times n plus 1 all over 2. Okay? Now, we want to know that. That's, especially if we're moving on to a calculus class, this is important. Okay, very important. So if we want to add up 1, 2, 3, 4, 5, well, let's just do an example. Let's say somebody asked us to say, you know, what do I get when I add up 1 to 50? Right? What do I get? What does this look like? Well, we know this is 1 plus 2 plus 3 plus all the way to 50. Well, one way to get that answer is to sit there and add those up. That's going to take very long. Another way to get the answer, right, is to use this formula. It's going to be n is 50, right? N, 50. So we're going to get 50 times 51, all divided by 2. That's 25 times 51, right? We know 4, right? We know 4 25s. 4 25s make 100, don't they? Right? 4 25s make 100. So this is 25 times 48 plus 3. Why did I do that? Well, that's 12 fours. Right? That's 12 fours. 4 goes into there 12 times. 12 times 25 is going to be, right? There are 12 fours in there, and every 4 makes 100. So that's going to be 1,200 plus 75. 3 times 25. So we get 1,275. Now, we can add really quickly if we remember this formula. So that's important formula number 1. Important formula number 2, I'll write it up here. What happens if we go k equals 1 to n, and we don't want to add up k, we want to add up k squared. We want to add up 1 squared plus 2 squared plus 3 squared all the way to n squared. And if you're asking yourself, where would I ever need to do this? I'm going to tell you right now, calculus. That's when you're going to need to do this. Well, there's a formula for this. The formula is n times n plus 1. I know, it's the same as we had here, right? But it can't be exactly the same, can it? So it's also 2n plus 1, and this time we divide by 6. Okay. So, big deal. Big deal 2. And here comes big deal 3. And maybe you can guess this one before I start. 1 cubed plus 2 cubed plus 3 cubed all the way to n cubed. Now this one, I know you look at the second one, you think, oh my gosh, the first one was kind of nice. I got that. The second one got kind of longer. Maybe I can remember that. You can't. Don't worry. This one, don't panic. It goes back to being nice. Now, it can't be that, can it? Because if it was that, it would be equal to this, and that makes no sense. The cubes can't equal what we would get when we multiply the numbers. Add the numbers themselves together. So this one turns out to be this. You square it, and you get the answer. Okay. All right, so that completes my lesson on 12.1. Now, I'm also going to record a lesson where I solve some of the homework problems from 12.1. It'll be a different video. All right? Hope everybody's having a wonderful day.